measuring the Young's modulus for a particular material. Like, draw this particular setup, and be sure to include markers which are 3 meters apart. The reason why they're going to be 3 meters apart is so that the precision of your measuring instrument, i.e. the meter stick, is much smaller than the length you're measuring, so that will reduce the percentage uncertainty in your measurement. So that's obviously a better measuring technique. They like quizzing you on things like this. Obviously remember, with both the Hooke's law questions, you get to an elastic limit, beyond which point it doesn't come back to its original length. So if you were to unload this graph here, you would end up coming back to some point along here, and that would be a plastic deformation. You also need to, I want to talk to you about these two graphs here. So you know the energy transferred to a spring is equal to the area underneath the force displacement graph. So if you get a spring and you stretch it like that, that's how much energy is transferred to the spring. If you get an elastic band and you put it under tension and you measure the loading curve, it will load like this. And so all of that area is the energy you've transferred to the elastic band. If you now take the weights off and you measure how it is unloaded, you will find it comes back like that. So that is the area of the energy which is being given back. So this bit in the middle is energy that's been transferred to the internal energy of the elastic band. That's why elastic, it heats up when you load it and unload it. Whereas a spring, if you load it and unload it, it won't heat up. So just with regard to an oscillation type question, if you put something into oscillation and it goes a spring into oscillation, don't say that the reason why it eventually dampens is because the spring is heated up. It doesn't. Hooke's law tells you that springs don't heat up because they load and unload along the exact same curve. Now, you need to sit down and make sure you just learn all of these, the definition for all of these: elastic, brittle, hard, durable, stiff, plastic deformation, tough, polymer, creep. And note glass is strong in compression but very brittle. Thing that enters into my mind very quickly is if something is malleable, that means undergoes plastic deformation under compression. If something is ductile, it undergoes plastic deformation under tension. So just remember, one is under compression, malleable, the other is under tension. Okay, we'll stop that one there.